Okay, so welcome again to Math 317. This is linear programming. And so what we're going to do today is we're going to talk a little bit about dual problems, a little bit about what kind of problems does linear programming solve and what are the techniques used to solve them. So just as a quick review, this was from the lecture you're supposed to watch because I was sick. What is a canonical linear programming problem? And so in linear algebra, we're trying to solve a system of equations. So we're trying to solve AX equals B. We often have the same number of equations as unknowns. And so if your matrix A is invertible, you get, oh, well, then X is just A inverse times B. And you have a really nice, explicit, theoretical way of solving the system. On a practical side, and this course is very much concerned with the practical side, you have to compute A inverse. Just because we write down the symbol A inverse doesn't mean we know how to actually do it. Well, we have algorithms to compute A inverse. The question is, how good are these algorithms? How stable are they? And as you start doing numerical calculations, depending on how the round-offs are, there could be some real issues. So, just because we can write down the solution in closed form as A inverse doesn't mean that it's a great solution. We have to make sure we know how to compute this well. Linear programming generalizes this. And so we consider, AX equals B, where we now have more unknowns than equations. So once you have more unknowns than equations, you should have many solutions. It is possible that I've given you an inconsistent set of equations, but that's very unlikely. If you have real numbers from the real world, odds are you will have multiple solutions. Well, when you have multiple solutions, now the question is which solution is best? And that depends on each person's preferences. So right now, I know we have a couple of people who are trying to decide which college is the best college for you, in the near future. Well, what are you going to use for your rating scheme? One could be location from home, and depending on how you view, close or far might be more desirable. Another could be, does it have graduate classes? Does it have a good faculty-student ratio? Does it have good extracurriculars? So different people will have different preferences. And so when you're trying to weight things, it's very important that you are clear on what you care about. We've talked about this is one of the reasons why we love to assign a monetary value to things, because it allows us to compare apples and apples. Later in the semester, we'll talk about how to deal with making choices when you have multiple things you care about, and you have to come up with some kind of conversion rate between the two. For now, however, we will assume that we have a linear function in the unknowns that we're trying to maximize or minimize. So that's going to be our function C transpose X, C1, X1 plus all the way up to Cn, Xn. It is possible to handle more complicated functions. We can handle quadratic functions, but a general objective function is very hard to do. And this is why it's called linear programming. We need essentially very good systems, very simple systems. So systems of linear equations, a system of a linear combination. Amazingly, a lot of things can be covered by this. So if you've seen logarithms in high school, that is not too surprising. If you've heard why we care about logarithms, that's a bit more surprising. This is something that's sadly not covered too often in high school as to why do we care about logarithms? One of the reasons we care about logarithms is logarithms convert nonlinear relations to linear relations. And so a lot of times, a method that initially only works if it's linear actually can be extended in much greater generality. All right, and then the canonical problem is we can assume that all of the variables are non-negative. As much as we may like, we are not going to be in a situation where we have infinite amount of money to invest or infinite amount of labor hours to allocate. Everything is always going to be finite. So by adjusting our variables, we may always assume that they are non-negative. We can always shift things if we want. So it's really not that big of a deal to have the variables non-negative. And in a lot of the problems that we're talking about, they're naturally non-negative. When you talk about how much food are you going to consume, you are not going to be consuming a negative amount of food. All right, the next one is that we can write everything as an equality. So when we were looking at the diet problem, so we needed to consume various amounts of food, And when you're consuming food, you need to make sure you meet the minimum daily requirement. Right? Is everybody making sure that they're meeting the minimum daily requirement? Are you writing everything down and making sure every day? You're playing with your lives, guys. Do you think it's hard or easy to meet the minimum daily requirements in every category? Especially here. You know, the desserts are really tempting. If I had more time this morning, I would have actually gone to Stop and Shop as well and picked up grapes in addition to the munchkins so that there'd be something healthy. This is why a lot of us have, vitamin supplements. Well, I actually have, healthy granola bars that have a lot of good stuff. I choose the healthy breakfast cereals. It might not be a bad exercise if you can for one day, look and see how close are you to meeting the minimum, daily requirements. Of course, when you hear the phrase minimum daily requirements, how good do you think it is to meet that? Do you think that should be the target? Or do you think it should be a little bit higher? Probably a little bit higher. It would be interesting, if you meet the minimum daily every single day, is that enough? One of the reasons sometimes the minimum daily requirement might actually be higher than you need, because a lot of times, the way people are, if you set it at a certain point, people might not quite make it to that, but if you set it a little bit high, they'll make it to where they need to. Has anybody ever been in an elevator? What's the first thing you do when you get into an elevator? If you're a paranoid person. Close the doors. What do you check? Okay, why? There's that, but what is the danger? We'll say pre-COVID, what's the danger? Well, not, okay, come on. Falls. Why might an elevator fall? It's too heavy. So they have the weight limit. Do you think that weight limit is exact, 2,000 pounds, that if there's 2,001 pounds, it's going to crash? Which way do you think they estimate? Do you think they over or underestimate how much you can take? Under, right? So if you go over by a little bit, it's not so bad. So a lot of times with constraints, you want to be very careful about which way are things going to be violated, how bad is it going to be? When they have traffic going over bridges, they have the bridges, you're having traffic, the weight limits are less than the bridge can take, so that if there's a little bit of a surge, they're okay. When you have a lot of things like COVID policies, a lot of times COVID policies are more severe than is needed because they know not all the policies will be fully followed, but if they set the bar here and people follow up to here, you'll still be at a safe place. So when we're looking at constraints, having this equality initially seems a little bit unrealistic. I don't know anybody who is so crazy, and I know a lot of crazy people, that make sure that they get exactly the minimum daily required amount of every single vitamin and nutrient. What do you think typically happens in terms of how much you get? Do you think you have exactly 100% of each? What do you think happens if you're doing a good job? Yeah, sometimes you get a little bit more. So having the strict equality would lead to, extremely hard to come up with a diet that's feasible if you can't exceed anything. Damn it, I got a little bit too much protein today. Now, the hope is that there's no real harm in exceeding. If you get 10,000 times the amount of protein, okay, that's probably bad. But if you maybe, 50% more, probably okay. So one of the ways you can handle something like this, and this was in the video, is you introduce some extra variables to take up the slack. And that way, it's not a big deal to convert from inequalities to equalities by just adding extra variables. So the whole point here is we want to create a mechanism to solve problems easily. If your problems have a standard form and you can immediately shove it into a black box and it spits out the answer, that's great. If I start singing -b plus or minus, can everybody follow along? Is this just ingrained in your memory what comes next after -b? Right? This is the quadratic formula. If I give you a polynomial of the form ax squared plus bx plus c equals 0, you immediately know how to solve it. If I give you a quadratic in a different form, it might take you a moment to figure out, how do I find the roots? Well, let me convert it to the standard form. And now that it's in the standard or the canonical form, I know how to solve it. That's what we're doing here. We're putting all of our problems into the same form. We could either maximize or minimize. If you want to maximize, that's the same as minimizing the negative of the objective function. So there's really no big deal between maximizing or minimizing. And so for definiteness, we always say we want to minimize. So this is the canonical linear programming problem. It's a nice exercise to show that no matter what I give you, I can convert it to something of this form. And then we're going to learn how to solve this. Now, it turns out that given any problem, there's a dual problem. So the dual problem has as its constraints y transpose A is less than or equal to C transpose, where the y's are real numbers, and we want to maximize y transpose B. So you notice that in the dual problem, we have a lot of the same characters as the original problem. We have the B from AX equals B. It's now occurring in the objective function. We have the C that was in the objective function now occurring in the constraints. Okay? Instead of using X for the variable, we're using Y as the variable. The big difference here is that we can't force an equality. We have a less than or equal to. All right, so this is the dual problem. So we'll talk in a little bit about why dual problems are so great. I'll jump here for now. I'll just jump to why dual problems are so great. So here's a simple number from the book. Let's assume you have a feasible solution to the canonical linear programming problem. What does a feasible solution mean? It means it solves the constraints. I say nothing about how good it is. So this is like, congratulations, you're set for next year. I've got you admitted to a college. Which college is it? Well, it may be a very bad college, but it's at least a college. If you own a movie theater, what's your objective? Make money. Almost any problem which begins if you own, the answer is make money. One of the few exceptions is if you own a sports team, what is your objective? It's not always make money. Win and make money. A lot of times people who own sports teams are more concerned, I want the ring, I want the title. But let's say you own a movie theater. You have to come up with a feasible schedule of showing movies on screens. And I've actually worked with the movie industry on this problem. If you're showing a movie on screen 1, you can't show the same movie on screen 2 at the same time. Different movies have different run times. They have different cleanup times. They'll draw in different amounts of people. They'll draw in different types of people. Who do you think movie theaters love? And who do you think movie theaters hate? They like people that get out quickly. Good. What else do they like? People who buy a lot of snacks. Movie theaters make a lot more money on concessions than they do on revenue. The way it typically works is the longer a movie's been out, the greater percent of the revenue goes to the theater. So in the first few weeks, a lot of the revenue from this showing of the movie goes to the owner of the film. Well, that's what most people want to go see the new film. So a lot of movie theaters will actually show older films very cheaply because, especially if you're in a hot place where people are just looking for air conditioning and make the money on the concession stands. So it's an interesting question for the movie theaters. Do you sell more in concessions? And maybe it's not worth buying some of these new movies with the very expensive contracts. Can somebody give me a feasible schedule of showing movies that will guarantee that there's no conflicts? That you're not going to have movies showing on multiple screens at the same time, that you're not going to have too many people coming in and overwhelming the people you have at the tickets. You're not going to have too many people leaving at once and overwhelming the crowds with exits or cleanup times. Can somebody give me a schedule that will guarantee that all constraints are met? It's a very simple constraint, a very simple schedule.
Older movies.
Nope. Very, very simple. Give me an assignment of movies that's so simple, it will satisfy every constraint I have. Nope, even simpler. 0. We show no movies. Every constraint is satisfied. It is a feasible solution. You will not say business long, but it's a feasible solution. If you're an airline and you're trying to come up with a feasible solution, you can't have one plane going simultaneously between 2 different cities. Once a pilot flies, they have to have a certain amount of downtime. You have to have a certain amount of students. Can you give me a feasible schedule for airlines? No flights. So a lot of times it's very easy to come up with an initial solution, an initial feasible solution. Amazingly, so many times the solution is do nothing. Sometimes, the solution is choose something randomly and do that. Then of the remaining choices, choose something randomly. Then of the remaining choices, choose something randomly. Frequently, we just need an initial starting solution to start processes. Once we have something, we can refine it and make it better. But we need a starting point. And amazingly, for many problems, the starting point is just do nothing. A lot of these problems are so bad that if you had every subatomic particle in the universe was a universe, and every subatomic particle in that was a universe of supercomputers devoted exclusively to you, learning since the dawn of time, that would not be enough to solve the problem by brute force. This is why this lemma is so powerful. What it says is if X hat is any feasible solution to the canonical linear programming problem, and Y hat is any feasible solution to the dual problem, then Y hat transpose B is less than equal to C transpose X hat. And equality holds if and only if X hat is optimal. So can anybody tell me why this is a useful lemma? So why is this useful? So why is this lemma so great? Good. You can see how close to optimal. And the second related to this is we have a check to see if optimal. And it is easy. So this is amazing. So imagine you own American Airlines. So your goal is to make money. This is not an easy job. You have to predict where people are going to want to fly months in advance and allocate your planes. You're going to have to decide which planes do you want to keep in strategic reserve for when there's bad weather or when there's malfunctions. Every plane in strategic reserve is a lost opportunity. You need to decide where to have your mechanics. You need to decide how many different types of planes to have. I think when Southwest came out, they only had one type of plane. So any mechanic could fix any plane, any pilot could fly any plane. You have so many constraints and you have so many parameters where you don't even know what the values are, and you have to optimize the problem. So it might take you, let's say there's been a remarkable advance in quantum computers and you have these available and you can find the optimal schedule after 50 years of computation. You can't wait 50 years before you start flying. So what you often do is say, well, I can afford to let it run for 5 hours, and then I'll take the best schedule I can get in 5 hours. And I actually had a problem like this when I was working with colleagues for the movie industry. We had 2 hours to give them the best schedule possible from when they got the list of available movies to when they had to tell the newspapers, these are the things old people read, actually print things out, what times the movies will play. And so we had to do the best we could in 2 hours. By having a simple test like this, you can get a sense of how close you are. Now, if there's a wide gap between them, that might just mean maybe you have a bad choice of the feasible solution for the dual problem. You might actually have a feasible solution to the original problem that is quite close to optimal. And you might just have a really bad feasible solution to the dual, and you might actually be really close. If, however, the two are very close, let's say they're within 1% of each other, okay, I'm within 1% of the theoretical best. That's not bad. Or maybe you're within 0.1% of the theoretical best. So that's a wonderful advantage of something like this, is that frequently it may be extremely difficult to get to the best solution, but we may be able to get to something very close very quickly.
Can you just go over really quickly the relationship between the dual problem and the original canonical problem?
Sure.
Are they like inverse?
They're essentially inverses. So if you do the calculation, essentially the dual of the dual is the original.
Okay.
So if you go through and you do the calculation very carefully, you return to where you start. And so a lot of what we're going to do today is talk about how sometimes when you're given one problem, frequently a related problem is easier to study. And this is a big theme in mathematics, is trying to find an easier problem to study. And so here, what's really nice about this result is that if you have this very simple condition to check how close is Y transpose B to C transpose X, that's very easy to check. And you get a sense of how close you are to the optimal solution. So there are a lot of problems in life that are very hard to solve, but are easy to check. One of my favorites is related to cryptography. So I'm going to give you two different methods of cryptography. So in the first method, I choose primes P and Q and their secret, say about 200 digits. I display their product N, and the password is P or Q. In the second, I let N be a random 5,000 digit number, and the password is N. Right, so we have two different methods. In the first, it's a 200-digit password. You have to get all 200 digits right, and I tell you, it divides N. In the second, it's 5,000 digits, and I don't give you anything. Which do you think is harder to crack, the first or the second? Do you think it's harder to guess the 200-digit password where I give you a number it divides, or the 5,000 digit? Which seems like it should be harder? The 5,000 seems like it should be harder. Given that I'm a math professor and I study prime numbers, which do you think is actually harder? Yeah, the 200. Now you could say, screw the fact that the password divides N. If I forget about that extra information, there's 10 to the 200 things to try. And the other, there's 10 to the 5,000. So if I just do it by a brute force attack, clearly the second one is going to be much worse. And the first one, I even have extra information. So it seems like the second should be much worse. How does the computer know if you gave it the right password in the first case?
Divide.
So it divides. So computer divides to check. So know it when I hear it. In the first case, does the computer need to know the password?
Like it needs to know the guess.
It needs to know the guess, but does the computer need to know P or Q? No. So what you can do is you can independently calculate P and Q, and they actually do this on separate computers, and then you destroy those computers. And now you can pass N to another computer. And that computer can be a gatekeeper. And that computer does not need to know the password to let people in. The computer only needs to know how to divide. You have a very stupid gatekeeper. It doesn't know the secret. What about the second case? How does the computer know if you have the correct passcode?
It checks what the password is.
So it checks memory. So if you will allow me to abuse the word, you can torture the computer. The computer, in the second case, has to have the password written, which means you have the opportunity to open it up and torture it. And that means that the second method is far less secure because the computer needs to know the password. So we are thrilled in mathematics when we discover things like this. So a lot of times in problems, it is very hard to solve a problem, but it is often very easy to check and see if you have the right solution. So going back to what we have, for the dual problem, if I somehow come up with a guess for the optimal solution, and I have a guess for the solution for the dual problem, and y transpose b happens to be c transpose x, I know I have the optimal solution. Doesn't matter how I got to it, I know I have it. So a lot of times we have these beautiful ways of, we can check and see if something is right. We don't know necessarily how to find that right answer, but if somebody gives us a candidate, we know how to check it. And that's what's so wonderful about this. So the proof is actually pretty straightforward linear algebra. So I've put it here in the slide so it's easily accessible. It's also in the book, and I'll just have you go through that. Okay. So what I want to do is I want to talk a little bit more about duality now. So I'm going to start off with something a little bit high level, then I'll go to a little bit more basic. How many of you have seen the Fourier transform? Okay, so if you've seen the Fourier transform, basically the derivative of f, we typically write f prime to show that it is related to a function. For the Fourier transform, we put a little hat to show that it's related. And so f hat of y is the integral of f of x e to the negative 2 pi I xy dx. And so this is just cosine plus I sine. As long as f has reasonable decay, this integral converges. Okay? And then there's a beautiful formula called Poisson's summation, which says, imagine, and this is not the most general conditions needed, imagine f prime and f double prime decay at least as fast as 1 over x to a power greater than 1. Then the sum of f over all the integers is the same as the sum of f hat over all the integers. When you see this, the question that should come to mind is, who cares? It turns out that this is extremely useful in a lot of problems in number theory and in probability. And one of the reasons it's so useful is that if you apply this to a Gaussian, so a Gaussian, bell curve, standard normal, you have a little bit of a freedom in terms of how you want to write things. The cleanest way to write it is if I write my Gaussian as like e to the negative pi x squared over n. So what's going on? This means I have a variance that's of size n, or a standard deviation of size square root of n. So this means my Gaussian is very fat. What this means is it's going to take a while before the probability starts to decay. If n is less than or equal to square root of n, this is essentially like e to the 0. So it's going to be essentially something of size 1. So for all values n less than square root of n, this has a significant contribution to the sum. Once you get up to like root n log n, it's small, but you've got to get up beyond root n before it starts to really die off. Look on the other side. When you do the Fourier transform of the Gaussian, the n in the denominator comes up to the numerator. Well, when little n equals 0, what do I get? So what's e to the 0? 1. When I take n equals plus or minus 1, I get e to the negative pi big N. That is tremendously small. The next term is going to be e to the negative 4n, then e to the negative 9n. Even if you use the geometric series to bound it, you get it tremendously small. And so you go from a sum that is very slowly decaying to a sum that's extremely well approximated by one term. It is very hard to get closed forms for sums. This is one of the reasons why we love integration, is if we give you nice functions, we have integrals that exist in closed forms. I can sum one term. How do you sum one term? That's it. There's nothing to do. So the whole point is that when you have a situation like this, in the limit, only the first term matters. And the second and everything else is exponentially smaller. So this is a great example of duality. Rather than studying a problem about f, we shift and we study a problem about f hat. For those of you who've seen Fourier transforms, how many of you have seen Fourier transforms with differential equations? So if you've seen that, it's another example of rather than solving the original differential equation, you take Fourier transforms, solve it there, and then you take the inverse Fourier transform and come back. So for a lot of problems, it is easier to study dual problems. So this is one of my favorite problems, and this should have been in the introductory video that you might have watched at the start of the semester. So imagine we have budget cuts, the money for the munchkins had to come from somewhere, and we only can afford a 5x5 chessboard. Does everybody know how queens and pawns move in chess? Queens can go diagonally, horizontally, and vertically. Pawns can only move forward and back. I want to put the 5 queens down on the board in such a way so that 3 pawns can be safely placed. So that's the original problem. So the question is, how do you do this? And then related to this is, what would be the generalization? So what do you think the general problem would be?
What position does a queen have to be to block on the board?
Well, I want the generalization of this problem. So the problem is, on a 5x5 board, place 5 queens so the 3 pawns are safe. What do you think the generalization of this problem is?
You want the queens to be.
So if you want the queens to protect the whole board, is there an easy way to put 5 queens to protect the whole board?
Just put them for each row.
Yeah, in each row, in each column, diagonally, there's lots of ways to do that. So one way to generalize it is, I want, instead of 3 pawns are safe, I want no pawns to be safe. Well, it turns out that problem is going to be easy. It's a generalization, but it's not the right one. Can somebody give me another generalization for this problem? So whenever you see numbers, you want to say, how can I change the numbers? So n queens on an n by n, and then how many pawns can safely be placed? So do you think 3 pawns can safely be placed on this? Yeah, the way the problem is written, it seems like you should be able to do that. Do you think you can do 4 pawns? Probably not, or I would have asked you to put 4 pawns down safely. So one thing when you see a problem like this is build intuition. N queens on n by n, how many pawns can be safe? All right, what's the simplest n we should start with? 1. This is not going to be, this is not going to be very hard. There's only one choice. And the answer, 0. All right, let's take n equals 2. How many ways are there to put 2 queens on a 2x2 board? So how many ways could we put 2 queens on a 2x2 board? How many places are there for the first queen? 4. How many for the second queen? 3. So it looks like there's 12 possibilities. So 12 options, but by symmetry, how many? 2. So there's really, how many ways are there to put the first queen down? There's really only one way. I have to put the first queen here. That's the only possibility. Oops. One thing. Okay, so if I look at symmetry, without loss of journey, I can rotate the board so that the queen is in the upper left corner. How many places are there now to put the next queen up to symmetry? So how many spots do I have for the next queen up to symmetry? So 2. What are the two possibilities?
To the right of the queen and then diagonal.
Okay, so I could go to the right of the queen, which is the same as going below. Or I could go diagonal. So there's only two possibilities by symmetry. This is a lot easier to check than going through all 12 possibilities. When you know, and the answer is still 0. All right. So now what if we do 3 by 3? How many possibilities are there for the initial 3 by 3? Up to symmetry. So, I mean, how many boards do I need to draw? 3. And the reason is all the corners are the same, all the middles are the same, and then there's the center. So without loss of generality, I can go queen, queen, queen. There's only 3 possibilities. Now, of these, the one on the far right is the easiest to do next. How many possibilities are there for this board? 2. And so for this one, so I could have queen, queen, or I could have queen, queen. I now even have to start worrying about how to do the next one. So this is where it would be really helpful to be able to write some computer code. In this case, are there any spaces that are safe? No. So at this point, I don't even need to do any more work on this one. What about the other one? Is there anything that's safe? No, I don't need to do any more work for that one either. Right? So I'm already done with those cases. Now for this case, once I have the queen here, I could go here, 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 or here. There's 5 possibilities. For this one, there's also 5 possibilities. So these 2 are the same, these 2 are the same, 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 and same. So if you go through it, there's actually 10 possible opening moves in tic-tac-toe up to symmetry. This is how you can beat little kids at tic-tac-toe very easily. Yeah. You don't have to memorize all the possibilities. If you think about how many opening moves and how many responses are there in tic-tac-toe, you might say 9 times 8, that's 72. There's really only 12. And so it's not that bad to analyze tic-tac-toe completely. So if we want to do the 3 by 3 case, we can start doing this. And we see that there's 12 things to consider. One of the trees very quickly ends. And now we have 10 more cases to consider. Hopefully, when we start putting in some more of the queens, we'll realize that there is going to be a 0, and then we don't have to pursue anything further. So I think the answer is still 0 on the 3 by 3 board. So it's a nice exercise, do 3 by 3, do 4 by 4. For 5 by 5, you can't put down 3. So the first question is, at least on the 5 by 5 board, can somebody give me at least a pattern where at least one pawn is safe? Does anybody have at least a suggestion where at least one pawn is safe?
Put the queens in like 1 by 3, 2 by 3, 3 by 3.
Okay, what you said, 1 by 3?
Yeah, like you just box off a corner.
2 by 3?
Yeah. Just like continuing horizontally until 3 by 3, and then you start going up to 3 by 4. 3 by 5.
Okay, and what place is safe?
If the pawn is in 1 by 5,
No, 1 by 5 is killed by that center queen. So, all right, so let's get rid of that center queen and say, let's just move it to some place that doesn't attack the spot 1 by 5. So let's tweak your solution. So we just need to put it someplace that's not on that main diagonal and not in row 1 or column 5. So we could put it there, right? And now we can safely put a pawn here. Is there any other place where a pawn can be placed safely? Yeah, through 4. So we know we can do at least 2. And so, one of the questions is, can you do 3? And if so, how? What happens on the general n by n? Can you give me an upper bound? And it can be a stupid upper bound. Can somebody give me a stupid upper bound on the number of pawns you can place? N squared. That is a stupid upper bound, right? Why is n squared an upper bound? You only have n squared spots on the board. You clearly can't do better than n squared. Can you give me a lower bound? What's your lower bound? 0, right? You're not going to have a negative number of pawns. So the question is, when n gets large, can you give me a non-trivial lower bound? Could something like this be generalized so that you'll always get some number of pawns safe? As you go higher and higher up, what if you try to put the pawn somehow in the corner? That's going to give you a square that's of size square root of n by square root of n. So maybe that's going to leave a lot of squares open. And again, sometimes small values can be very misleading. So the actual answer is quite surprising in terms of how many pawns you can safely put down as the board gets bigger and bigger. So now let's try to think about a brute force approach. How many spots are there for the first queen to try? Without symmetry, n squared. So it would be 25 times 24 times 23 times 22 times 21. With a very minor symmetry, we could improve to 25 choose 5. We're choosing 5 spaces out of 25. Order doesn't matter. So this gives us old answer divided by 5 factorial. That's a nice improvement. And as n gets larger and larger, that's going to be better and better and better. But it's still going to be very bad as the board gets bigger and bigger. Your products grow quickly. And this is, of course, throwing away a lot of symmetry. How many opening moves are there for the initial queen on a 5 by 4 and a 5 by 5? So how many initial places are there to put the first queen by symmetry? On a 5 by 5 board, how many distinct squares do we have? So there's 25 squares, but some of them are the same if we rotate or flip. So how many distinct squares are there? On the 3 by 3 tic-tac-toe board, there was only 3. What is it going to be on the 5 by 5?
7.
Why 7?
I see the corners.
Okay.
5, 2.
So 1, 2, 3, 4. 1, 2, 3, 4. All right, so the corners is 1. What's next?
And 1 into the corners. So that would be like row 1, column 2.
Okay. So those would all be 2s.
The middle row. On the top.
So that would be a 3.
And then the corner down from on the other.
So that would be a 4. Then the middles would be 5. And so the answer is 6. So there's really only 6 initial spots. So rather than saying 25, there's actually only 6. But then you would need to somehow figure out how do I nicely choose now the remaining. And it might become so much of a pain to code the symmetry that it may not be practical. But if you're just putting down the initial. All right. So what was the main thing we were studying today? Was duality. Instead of placing 5 queens so that 3 pawns are safe, what do you think we should do? So instead of placing 5 queens so that 3 pawns are safe, what do you think the dual problem would be? 3 queens so that 5 pawns are safe. Then change queens to pawns and pawns to queens. So this is the dual problem. How many ways are there to choose 3 squares out of 25? It's 25 choose 3 versus 25 choose 5. So that's much better from a computational perspective. So this is an example of the power of switching to the dual problem. Is often the calculation is a lot easier, and then you can go from that back to the original. All right, so this is a good place to stop.